For the first part of this project, I'll be using the graph x equals 12 sine t minus 3 sine 6t, and y equals 12 cos t plus 3 cos 6t, which looks like this. Now, changing the step function can have a number of effects on the graph. 0.1, which it's at right now, is generally a good value to start with because the calculator will plot points at each interval of that step. So for 0.1 it will plot it at t equals 0, and then 0.1, and then 0.2, and so on. If you make this step smaller, it just means there'll be more dots plotted, which results in a smoother graph, but as there are more points, it will take longer to graph. So I'll change the step to 0.05 to show that. Now, if you increase the value of the step, it will do the opposite. Less points will be plotted, and it will be less accurate, but the graph will complete a lot faster. So if I put the step at 0.2, this is what it looks like. Now, if you make this step too high, you won't even be able to recognize the graph, as there won't be enough points to show the shape accurately. So even if I were to put the value of t at 1, the graph won't look anything like it's supposed to. And if I make this step way too small, or if I were to make this step like 0.0001, it would just take forever to graph, even though it would eventually show what it looks like. Changing the domain of t will basically affect how far the graph goes. In this case, since a full rotation of a circle is 2 pi, a domain of 0 to 2 pi will result in a full rotation of the graph. If I put the domain from negative 2 pi to 2 pi, the graph will complete 2 rotations. So I'll see if you can see it. And then it continues going around. You can probably see it going over some of the lines, but it does complete 2 full rotations. You can also cut the graph off and at any point really, but for instance putting it at pi instead of 2 pi will cut the graph off at halfway, like this. And you could do that for any value and make it go around as many times as you wanted, or not even complete a circle or a full rotation. For the next set of questions, I'll be using just a circle, which is x equals cos t, and y equals sine t, which will right now just look like a circle with a radius of 1 right there. These rules can work for any parametric equation, but it's a lot easier to see what happens with just a circle. If you want to bend or stretch this, you have to adjust the coefficients of the x and y components. If you want it to still be a circle, you can just keep both of them the same. So, such as 8 cos t and 8 sine t will stretch it 8 in both directions, which essentially just makes a circle of radius 8 instead of 1, like this. If you adjust the coefficients to have different values, it won't be a circle anymore, as you've stretched it either way differently. So if x is 9 cos t and y is 6 cos t, it will be stretched 9 in the x direction and 6 in the y, so it'll look like an oval. And then to move a picture around the grid, so if we go back to just the circle with radius 8, to move this around the grid, you simply have to add a constant on the end of the x or y component, or both. So if you wanted this circle to move, if you wanted to move 4 units right and down 2, all you would have to do is add 4 to the x to make it go 4 right, and subtract 2 from the y to make it go down 2, and that will look like this, which is still the same circle, just translated 4 units right and down 2. For 3D parametric equations, this calculator won't do it, so I will show what a simple one looks like on this thing I downloaded on my computer. So for this, I will put the equation as x equals cos, if you can see it here, x equals cos t, y equals sine t, and z, which is the third dimension of it, equals just t. When I press OK, it will graph it really fast, so I'll try and show you. That's that right there, but to adjust it, this is from 0 to 2 pi, so to get the full thing, I will put it at negative 2 pi to 2 pi, and maybe it will go slower if I put this step to something like 0.09, and then let's see what it looks like now. So this is just a spiral, you can see it all over the place.